Moving on to chapter 33. And what I thought I'd do is just stop for a second and just back up. So we learned a lot of right-hand rules. Let's just go over them real quick. So there's the flat right-hand rule. This is the last one we learned. This one tells us the direction of the force that charge or current moving in a B field feels. And so here we have some positive charges moving to the right, and there's a B field going up the page. And so we take our hand, our thumb goes with the positive charge, fingers shoot with the B field, and my palm points out of the page. And so the force on those charges is out of the page. So this one we want to use when we're asked about force. Our first curly right hand rule tells us the direction of the B field from a loop of wire. Okay, and so here's a loop of wire, and the way you do this is you put your fingers with the green current. So my fingers stick around with the green current, and my thumb points right at me. So that B field is shooting right at me out of the page. And our other curly right hand rule tells the direction of B field from a wire in a more general sense. And here's the wire, and in this case it's switched. My thumb is now the current, and my fingers are the B field. And so as my thumb comes out of the page, my fingers curl in a counterclockwise direction, and that's the way the B field goes around the wire, counterclockwise. So far we've seen that moving charges create magnetic fields. All right, and we saw this in currents, and we saw that what basically accounts for magnetism is this happening at the atomic level. Currents in a wire cause this. We've also found that B fields exert forces on moving charges. So a current carrying wire will feel a force if it's in a magnetic field. And so chapter 33 is now about the final case of sort of connecting all this stuff, which is that whenever there's a changing magnetic field, it'll cause charges to move. All right, and Faraday's discovery, so this is the big law here is Faraday's law. So here's a little picture of his sort of experiment, and you've got a little coil of wire hooked up to an ammeter that measures current. All right, and he realized that if you move a magnet through that coil of wire, current will flow through the circuit. All right, now it only happens when the magnetic field is changing. So if you just put the magnet inside, the coil has no effect. So it's only when it's sort of going in or coming out that it has this effect. Okay, and so we're going to break this down and try to understand this. And so we're going to start with a case that hopefully we can make a lot of sense of. So here I just have a metal bar, and I'm moving the metal bar to the right with some velocity. Okay, now in the metal bar, you assume that there's charges. All right, now these charges are going to feel a force. And so if I do my right hand rule, the flat one, which is for a force, if my thumb goes with the velocity, my fingers are pointing into the page, which is the way the B field goes, and then the force is upwards. So a force, a positive charge, would feel as upwards. Now in real life, in a piece of metal, the electrons are what moves. And so what happens is the electrons move down, but it's kind of the same result. Okay, and so the result here is that the electrons move down, which leaves a positive charge up on the top. All right, so we have a positive charge up here and a negative charge over here. And this comes because these charges are moving in a magnetic field. And we call this motional EMF. Why do we call this that? Well, because anytime you separate positive and negative charges, all right, you kind of have a little tiny battery. All right, and so there's going to be an electric field pushing down, all right, and so it's a motional EMF. And so by moving this in a magnetic field, we've made a little battery. We have a positive side and a negative side, all right. And basically this will keep happening until the point where the force from the magnetic field is exactly balanced by the force of the electric field. So again, I have a bunch of positives up here on one end, a bunch of negatives. There's an electric field pointing this way, and so a positive charge, the force I feel from magnetism is upwards, the force I feel from the electric field is downwards, and these will cancel out, and then the charge will stop flowing. So we can learn a little bit of things about this. Okay, first of all, what we can do is we can equate the two forces. So force of electric equals force of magnetic, and we know that the force of electric equals charge times electric field, and for the force of the B field, that's QVB. Now there would be a sine theta, but we're assuming here that it's 90 degrees, okay? The velocity is 90 degrees from the B field. And so what happens is when the charge cancels, we get this relationship, E equals V times B. Okay, so this is what the relationship that has to happen in order for these to balance. So the electric field you form when you do this equals velocity times B. And what we do here is, since we know that it's a conductor of length L, we can use one of our equations from before to actually solve for our voltage. Okay, so our voltage is going to be our electric field, right? So we remember the voltage equals our electric field times our change in distance. Okay, that's the case that what essentially you have is kind of a little capacitor here. And so our electric field is V times B, and the distance that this is happening over, we're calling the distance L. And so the voltage, which another way to call voltage is EMF, looks like this right here, VLB. So when I move this bar in a field, charge separates. Whenever charge separates, we can think about it as being kind of like a little battery or a capacitor. All right, and the voltage that we have in this little battery equals V times L times B, and hopefully that makes sense. The faster you move it, the stronger this battery will be. The longer it is, the stronger it will be, and the harder, the more intense this magnetic field is, the stronger it'll be. Let's look at a picture. Here's an example now. So here I have a metal bar moving in a magnetic field. I want to think about this and see which way will the charges align themselves. So pause this, give this a try, and see what you think. All right, this one's kind of a trick. You'll see that there is no force here. All right, if you remember one of our foundations, so the force from a magnetic field is the QVB sine theta, where the sine theta is the angle between the velocity and the B field. And here, that angle is 0. So sine of 0 equals 0, and so the force is 0. Another way we've talked about this is that whenever the velocity and the B field are in the same direction, there's no force. There's no force on the charges, and so this bar won't have any charge distribution on it. All right, and then what we like to do is set up a little situation like this. And so this is kind of a little weird U-shaped wire situation. They talk about this a lot. And basically, this metal wire here is sort of free to move back and forth. Okay, and so here they're sliding it to the right. And so what we've been talking about happens. A bunch of positives line up here, a bunch of negatives line up here. And now, since this is sort of hooked up to a wire here, a little U-shaped wire, that gives the charges a chance to move, and so a current will flow. And so current will flow, and in this case it'll be in the counterclockwise direction. All right, and we call this an induced current, like kind of like we were talking about with the very first slide. Okay, and basically the key here is that anytime you have a wire loop like this over here, where the magnetic field inside changes, you're going to have an induced current. Okay, that's sort of the basis of Faraday's law. But we're looking at it here very much in terms of just what the charges are doing. So because I'm moving this bar in a magnetic field, the charges separate, and then they'll actually have a current flow. And the thing is, if you go back to Ohm's law, current equals our voltage, which is the EMF in this case, divided by the resistance. And so if my current, if my little setup here has a resistance of R, then this will be my current here. So VLB divided by R. Another thing that's interesting is if we look at this here, okay, so now there's a current flowing in our bar. So we talked about how there's a current flowing in the bar, and the current is flowing in this direction that's counterclockwise, which means it's going to be going up right here. If I do my force on this, so if I put my thumb with the current, put my fingers in with the B field, the magnetic force on this current is backwards. Okay, and hopefully that makes sense to you. But what's happening here is, to do this, I need to keep pushing really hard this force of the pull. Okay, and so when I do this, there's a force backwards that makes it very hard to do this. Because you think about it, to make this current flow, you're making energy flow. And so there's always a force that goes against you to make energy, right? Because you can think about it, you could oil up this wire on both sides really nicely so that it was really slick, and you can give this thing a push, all right, and it could go for a very long time, but because there's a force going against it, it won't be able to do that. And so it's really hard to do this. And so while you're doing this, you have a power, and the power is basically dissipated by the resistance in the circuit. And this is our induced current, and so this is a device that converts mechanical energy to electrical energy, and we call that a generator. So by moving this bar, I make a little battery, and that little battery will make a current flow. Okay, and here they've done the other direction. Okay, so here they're pushing it backwards, And so if you do your right hand rule, your velocity would be to the left, your finger is pointed and your palm is down. So the positives go over here, and the negatives go over here, and current flows in the opposite direction. So let's give this a try. So here we have one of these weird U-shaped wires, all right, and I'm moving it in some kind of a magnetic field, and current flows in this direction, which is clockwise. I want you to think about it and see which way does the magnetic field have to flow. So pause and give this one a think about. All right, so I got that it was into the screen. So if you look at the setup here, the way the current is flowing, that means I want positive charges up at the top and negative charges at the bottom. So the current, remember our conventional current flows from positive to negative. And so if I do my right hand rule, the velocity is the green line right here, and I want the force, remember the force, your palm is the force that the magnetic field pushes on the positive charges. I want that to be up. So if my thumb goes with the velocity and my palm points up, if I do that, my fingers are pointing into the screen. Okay, so hopefully we have a feel now for some of how this happens microscopically. Now in general, it's very difficult to look at all these examples microscopically, and so we developed some tools to calculate these kind of quicker. And the first tool is going to depend on what we call magnetic flux. All right, and Knight has this nice way of talking about it, and he says, imagine holding a rectangular wire loop, okay, that's got an area of A times B in front of a fan. The volume of air flowing through the loop depends on the angle between the loop and the direction of the flow. Okay, and so this is kind of a definition of flux. And so he talks about the area effective, which is kind of a weird concept. But basically, the area effective is sort of the area of the loop that the fan sees. Okay, and you calculate that by doing the area of the loop, which is A times B times cosine theta. And so let's see some examples of how this works. So here's the picture, and so this loop is switching, okay, and basically he talks about sort of three different cases. Okay, the first case, when theta is equal to 0, okay, that's where the fan is totally going through it. When theta is 90, okay, and that's where no air is going actually through this loop at all, and then some tilt angle in between the two. All right, and this again is sort of talking about the definition of flux. And so here's the three cases. So when the angle is 0, here's the angle is 0, all right, the air is going through sort of in a maximum case. The maximum amount of air going through is possible. Here's sort of the head-on view as if you were looking from the right on. Here's the tilt angle. So if you're looking from the fan basically has less air going through. One way to quantify this is sort of how many arrows you see. So here I have a total of 9 arrows, here I have 3. And finally, when it's flat, there's no air going through it at all. So this is a sense, gives us a sense of what flux means. All right, and when we talk about magnetic flux, it's the same idea, but instead of wind going through, we're talking about magnetic field lines going through. Okay, and so here's an example of the same sort of three cases. Theta equals to 0, theta, and theta equals to 90. And so here you can see there's a bunch of magnetic field going through. Here there's a little bit less because the tilt angle has made it smaller, and here it's completely 0. All right, and so our rule that we're going to look at as far as how this works is that the magnetic field going through a loop, when that changes, it's going to make one of these induced currents. And so this is our way of quantifying how the magnetic field changes. And again, another way to think about this is how many magnetic field lines are going through your loop. And so here there's a whole bunch of magnetic field lines going through my loop. Here there's less, and here there's 0. So our definition for this area, the area effective, will be a vector technically, okay? And so Knight will talk about this. And so the vector is basically 90 degrees to the surface of the loop. So here's our loop. The loop makes some plane, and this vector, the area vector, is perpendicular to the loop, okay, the actual direction of it. And the magnitude is just the area. So in this case, for a circle, if you call this r, it would just be pi r squared, okay? And so finally, our fundamental definition that we call magnetic flux is what, again, Knight calls the area effective times the magnetic field. So it's basically the area times the B field and then cosine of theta. And theta is the angle in the little picture, you can see it here, between the area vector and the magnetic field. So that's the area, that's the angle there, okay? And the units for this are what we call Webers. which is going to be units of magnetic field Tesla times area, which is meters squared. And so here we have a case of two situations, two loops, all right, and we have magnetic fields. In part A, the magnetic field is twice as strong as part B, and I want to know which loop has the larger magnetic flux going through it. So the field is twice as strong in A, and the square is twice as wide in B. So think about this, pause it, and figure out which one has more magnetic flux going through it. Okay, hopefully you got that it was loop B. And so if we think about this, there's a couple of different ways to think about it, but the magnetic flux is our area times the magnetic field times cosine of the angle theta. And so first of all, in both these cases, the theta is just 0 because the magnetic field and the imaginary area vector are both in the same direction. So this basically just equals the area times the B field. And so what happens here is in the first case, the B field is stronger and the area is smaller. And in the other case, it's switched. Okay, and so we got to think about this. And so if in first case A, okay, I'm going to say that the B field, I'm just going to call it B, and then I'm going to call the length of this guy here to be L. And so it's B times L squared would be the flux. In the second case, the B field is half as strong. So the B field would be B divided by 2. However, the length is twice as long. And so, but it's 2L squared. Okay, because here, so the length here is 2L, but to find the area, I've got to square that because we've also made this side here twice as long too. And so when it's all said and done, I'll get B over 2 times 4L squared and 2BL squared. So the second case is bigger. Another way to think about it is, again, when we talk about flux, one way to talk about it kind of roughly is that it's the number of magnetic field lines. So here in this square, there's 4 magnetic field lines, and here there's 6.